We've been graphing cosine and sine, looking at those graphs, doing shifts vertically, reflections across the x-axis, and then also looking at effects of the period. And so now what we're going to be looking at are graphing the other trigonometric functions: tangent, cotangent of x, cosecant of x, secant of x, and also doing these transformations, stretching them, reflecting them, working with them vertically. So before we jump into these trigonometric functions and graphing them, just recall that we get vertical asymptotes, because all of these are going to have vertical asymptotes. So recall vertical asymptotes, I'm just going to call it VA, vertical, short for vertical asymptotes. They occur at values which set the denominator equal to 0, but not also the numerator. So vertical asymptotes occur at values let's set the denominator equal to 0, but not also the numerator. If it sets both of them equal to 0, which we're not going to really, I don't think, deal with in our situation, but if they set both the numerator and denominator equal to 0, then it's a hole. It's undefined there, but it's a hole in the graph versus a vertical asymptote. Okay, so and recall, if we're looking at vertical asymptotes, my pens are really huge. Let me just also do this. What's happening on the graph, and normally we denote that vertical asymptote with a dotted line. What's happening on the graph is that graph is hugging that line but never crossing it and shooting off to positive or negative infinity. So in this case, if this was A, we have a vertical asymptote at x equals A. And as x is approaching A on the left, we're saying that's shooting off to positive infinity. It looks like something like this. And as x is approaching A on the right, it's also shooting off to positive infinity. So the reason why this is important is that all these trigonometric functions are written as quotients, and we have a variable in our denominator. And so all of these trigonometric functions actually have vertical asymptotes. So I think the easiest ones for me to graph are the cosecant and secant, because basically those are based off of the graph of sine and cosine. I'm going to erase what I have in here. Okay, so let's look at just graphing cosecant of x. And while we're doing that, we'll discuss what's going on. So here we have y is equal to cosecant of x, and we want to graph this. So let's first rewrite this in terms of sine or cosine. In this case, this is the same thing as 1 over sine of x. And so we need to worry about values which set our denominator equal to 0. So sine of x cannot equal 0. These are values that we would exclude from our domain because those are inputs that don't give us back a real number. And these are also values where we're going to have vertical asymptotes. And so we want to look at when does that equal to 0? What values of x? And if it helps you to look at the unit circle to help you to look at that, then go ahead and do that. So recall that sine of x was equal to the y value on the graph. And so the y value is equal to 0 when we're hitting this x-axis on the unit circle. And so there's multiple values which set that denominator equal to 0. So when x is equal to 0, sine of x is 0, so x cannot be 0. If we loop around, so when x is equal to pi, 2 pi, etc. And also you could go the opposite direction, right? So clockwise, this would be negative pi, negative 2 pi, etc. So a way that we can write this, so our domain are all real numbers except when x are equals to that. So we looked at set builder notation. So that's where we have that curly bracket. X, that vertical line means such that all values of x such that x does not equal. And so let's write that mathematically. And so this is the same thing as k times pi, where k is equal to an integer. And a way to write that integer set, which is like kind of that funky z with the extra line connecting the horizontals of the z. Okay, so that's our domain, but those are also where we're going to have vertical asymptotes. So we have vertical asymptotes at x equals k times pi. So notice if we graphed sine of x, those are also the values, right? That it's where it's crossing the x-axis. Let's just graph sine of x really quickly. And so if we're graphing sine of x, recall, it started at the origin. We labeled our values where we're cutting it into sections of quarters of a period, and a period is 2 pi. So we had pi halves, pi, 3 pi halves, and that gave us 1 period. And so graphing this, we started at the origin, we went up to pi halves to 1, then we got to pi, down to 3 pi halves, up to 2 pi. And this was equal to our sine function, or 1 cycle, and it would continue. So again, our vertical asymptotes, those were the values where our graph of sine of x is crossing the x-axis. And so these are our vertical asymptotes. Let's just put those on our graph that we just graphed sine of x. Those are the vertical asymptotes of cosecant of x. So we have an infinite number of those. And so now let's look at some important points here when we're graphing this cosecant of x. And so recall, let's go back actually to sine. Sine was equal to 1 at pi halves. And so if we were looking at cosecant of x, we have at pi halves, we have 1 over sine of pi halves, which is 1 over 1, which is 1. So we get this point here. That's kind of at that maximum of that peak of sine of x. And then if we start plugging in values like pi fourths, we would have root 2 over 2 and 1 over root 2 over 2. That's actually a smaller number than 1. And so 1 divided by a smaller number gets larger. It ends up that it kind of looks like a parabola shape that's off the maximum of our sine of x. And it's growing and growing and getting closer and closer to those asymptotes. So same sort of idea here. When we put in 3 pi halves into cosecant of x, that's 1 over sine of 3 pi halves, or 1 over -1, which gives us back -1. And so what the graph of cosecant of x is going to look like at that point is it's going to look like a upside down parabola shape that is growing. It's going down to -infinity as we approach our vertical asymptotes. And so we can just base off of where our max and mins are of sine of x, where it's crossing the x-axis, we can get the shape of cosecant of x. So if I got rid of sine of X. And this would be what the graph of cosecant of X looks like. And so it's really helpful to be able to graph these reciprocal functions of cosecant of X and secant of X to get us the graph of the functions we want. So other things that you should be able to answer on these type of questions, what the domain is, what the vertical asymptote is. You should also be able to find the range. And so the range, recall, are the values of y, those outputs that we're getting for every input that we put in. And so the y values that we're hitting, notice that our part of our graphs is shooting down to negative infinity. So we're hitting all values from negative infinity. And then notice that we have a max here at -1, including -1. So we're going to put a bracket union. So there's a jump in the graph that we're not hitting any y values. So we need to exclude those. We're not going to put those in there. And so our next, our minimum of those parabola shapes, notice, is our y value of 1. And so we're hitting 1. We're including that because 1 is an output. And then our parabola shapes are shooting up to positive infinity. So it's going to infinity. So this would be the range of cosecant of X. So when we have shifts in our graphs, then basically, again, we're going to use the base of our reciprocal function, sine of X or cosine of X, depending on which trigonometric function we're looking at. We're going to look at those shifts and reciprocals and use the picture of that function to help us graph cosecant of X or secant of X. So we're going to graph y equals secant of X. We're going to look at finding the domain, the range, and the vertical asymptotes. So first, let's rewrite this in terms of the reciprocal function. In this case, secant of X is 1 over cosine of X. So y is equal to 1 over cosine of X. We can't divide by 0. In this case, when cosine of X is equal to 0, this is where values we have to exclude, but they're also where our vertical asymptotes are going to occur. So we want to look at, when is cosine of X equal to 0? So again, if it helps you to look at the unit circle, you can do that. And if we look at the unit circle, recall that cosine of X was the X value of the point on the unit circle, depending on the angle. And so the values where X is 0 are when we're on the Y axis. And so those are values where X is equal to pi halves. Three pi halves. So if we loop around clockwise, counterclockwise, in this case, 3 pi halves. So if we add a pi halves to 3 pi halves, sorry, we're adding pi, we're adding pi to 3 pi halves. So that's going to give us 5 pi halves. That would get us back up to the coterminal angle of pi halves. And so we can keep looping around. 7 pi halves. So these are going to be where vertical asymptotes occur, but we can also go in the counter or the clockwise direction. And so those are also values where X is equal to negative pi halves, negative 3 pi halves, etc. And so notice that this is pi halves plus pi, or notice it is an odd integer always in front of that pi. And so a way that we can express an odd integer, well, if you take an even number, and an even number could be expressed by 2 times an integer, and you add or subtract 1 to it, it doesn't matter. That's always going to give us an odd number. So 2k plus 1 all times pi halves. This is values where we're going to have vertical asymptotes. And those are also values that we have to exclude from the domain. So the domain's going to be all real numbers except these values. So the set x such that x does not equal an odd integer 2k plus 1 times pi halves. Again, k is an integer. So let's use that fact. Let's graph cosine of x. And then based off of graphing cosine of x, we can get secant of x. And so let's put those values on the x-axis. And so again, a normal period for cosine of x is 2 pi. So let's break that into quarters. So we have pi halves, pi, 3 pi halves, and 2 pi. We'll go the other direction, negative pi halves, negative pi, negative 3 pi halves, and negative 2 pi. Recall our maximum, our amplitude of cosine of x was 1. So our maximum is 1 and our minimum is negative 1. And cosine of x, that started at our maximum value. And so we're going to start at the point 0, 1. Or if you look at the unit circle, at x equals 0, cosine is 1. So at pi halves, this was our x-intercept. This was when cosine was equal to 0. Then at pi, we have negative 1, 3 pi halves, we're back up to 0, 2 pi, we're up to 1. Negative pi halves, we hit 0, negative 1. At negative pi, negative 3 pi halves, we're back up to the x-axis, and negative 2 pi, 1. So this was our graph of cosine of x. So where the values hit the x-axis, those are where our vertical asymptotes are going to be for secant of x. Let's just put our dotted lines there. And same sort of reasoning. When we graph this reciprocal function, secant of x, from cosine of x, we're just going to find our maximum and minimums of our cosine of x function. And that's like the vertex of that parabola shape. And it's going to be hugging those vertical asymptotes. And so we have our graph of secant of x, and we can just get rid of our graph of cosine of x. Let's see, just secant of x in there. And the last piece of that question, we want to find the range. Same thing in here. Our range are all the y values. And so we're coming from negative infinity, hitting negative 1 is the biggest y value that's occurring. And then there's a gap where we don't hit any y values, and then we get 1 to infinity. So union 1 to infinity. So there's different ways that you could express that. We could have said that y is less than or equal to negative 1. Union y is greater than 1. Greater than or equal to. Or you could technically write this as y is greater than or equal to the absolute value of negative 1. So recall to drop the absolute value, not negative 1. well, I guess that would be okay because the absolute value of -1 is 1, but the absolute value of 1. Basically, to drop our absolute value of a inequality when it's greater than or equal to, you would rewrite your inequality like what we have up here above. So just kind of a review on different notations. So that's how we're going to graph secant of x. And so again, now we can deal with these ones that we've been graphing before with these transformations and graph these transformations of secant of x and cosecant of x. So let's look at a couple of those examples. Okay, so we want to graph y equals -3 secant pi halves of x. And we're going to find the domain, the range, the period, and the vertical asymptote. So let's rewrite this in terms of sine or cosine. Well, secant of x could be rewritten in terms of cosine of x. So this is going to be y is equal to -3 all times 1 all over cosine of pi halves x. And so let's graph the reciprocal function y equals -3 cosine of pi halves x. And based off of this graph, we can get the graph of our secant function. So recall we looked at finding the period. We found the period by looking at the argument. So our argument in this case is pi halves x, and sandwiching it in between one period, a cycle. So we could say 0 is less than or equal to pi halves x is less than or equal to 2 pi. So that's a normal period of cosine of x. And so let's find our new period. And we would do that by finding what x is in between our inequality. And so we can do that by multiplying everything through by the reciprocal of pi halves, which is 2 over pi. 2 over pi times 0 gives us 0, is less than or equal to 2 over pi times pi halves, that's 1, leaving us with 1x, is less than or equal to. So notice here our pi's are going to cancel when we distribute that 2 over pi times 2 pi. The pi's cancel and we're left with 2 times 2, which is 4. So we know that our period has a length of 4. 0 to 4 is 4. So once we did that, we found out our period. From that inequality, we know that the start of one cycle of our period, we could say, is 0. The end value of one cycle of our period is 4. We looked at our quarter value, our half value, and our 3/4 value, and plotted those on the x-axis to help us graph these. And so our quarter value, or half value between 0 and 4, half of that is 2. Our half value between 0 and 2, which gives us our quarter value, is 1. And our half value between our halfway mark and our end mark is 3, 3/4 value. So graphing that piece, we have 1, 2, 3, and 4. So normally our cosine function starts at 1, but we have some effect here by this -3. Our amplitude of cosine of x, going back to amplitude of cosine of x and sine of x, that was the absolute value of the coefficient in front of what we were multiplying cosine or sine by. And so this case, the absolute value, and we called it A, of -3 is 3. only cosine of X and sine of X, cosine functions and sine functions have amplitude. The other trigonometric functions do not have any amplitude. That amplitude told us how much we were going to stretch vertically that cosine or sine function. And so in this case, normally we would have a amplitude where you go up to 3. In this case, actually, there's no shift. So we're going to go up to 3 would be the maximum of our cosine function, and -3 would be the minimum of that cosine function. But because of this negative in here, that negative in front of the 3, this reflects it across the x-axis reflection. So for this cosine function, we're starting here at 0, -3. At 1, we're going to hit the midway line, which is our x-axis. At 2, we're going to hit the max at 3. 3, go back down to the midway line, x-axis. And at 4, we're hitting the y value of -3. And plot those important points. And that gives us the graph of our cosine function. So these values where we're crossing the x-axis, these are values which are setting our denominator equals 0 for that secant function. And so for the secant function, our vertical asymptotes are at the equation of the lines x equals -3, -1, 1, 3. So those are odd numbers. So vertical asymptotes at 2k plus 1, where k is an integer. Let's write those vertical asymptotes or denote them by a dotted line, which aren't really there, but helps guide us graph. So our graph can never cross a vertical asymptote. And then based off of our maximum and minimum values of this cosine function we just graphed, we can get the graph of this secant function. And those are going to be either the max or the mins of this secant function. And so the graph of -3 secant of pi half x, let's just take away now that graph of cosine of x. So we just see the appropriate graph. So we got our vertical asymptotes. Our domain are all values except for those values which give us our vertical asymptote. So our domain are all reals, all real numbers. So that capital R with the vertical double bar line is representative of real numbers, except x cannot be 2k plus 1. Where k is a integer. Our range, so our y values here, those are -infinity to -3, including -3, union bracket 3 to infinity. Okay, so we've answered all the questions. We got our graph, domain, range, period, and vertical asymptotes. of that secant function. Okay, so looking at the following, we have y is equal to 2 cosecant of 1/4 x plus 1. Let's graph this. But before we graph this, let's graph the reciprocal function of cosecant x, and that's going to be, we're going to want to graph y equals 2 sine of 1/4 x plus 1. So let's look at our period. Our period is being affected here because of this 1/4 of an x. So let's sandwich the argument 1/4 x in between a normal period cycle 0 to 2 pi. And so now solving for x in between, we could multiply both sides of that by the reciprocal of 1/4, which is 4. So multiplying each side of the inequalities by 4, we get 4 times 0, which is 0, is less than or equal to 4 times 1/4 x is x, is less than or equal to 4 times 2 pi is 8 pi. So we're going to start our period at 0. We're going to end one period at 8 pi, figuring out the quarter mark, the halfway mark, and the 3/4 mark of that one period cycle. Well, halfway between 0 and 8 pi, I can see is 4 pi. Halfway between 0 and 4 pi is 2 pi. Halfway between 4 pi and 8 pi is 6 pi. And so those are important features on our graph. So let's label those. Two pi, 4 pi, 6 pi, 8 pi. So negative x values, negative 2 pi, negative 4 pi, negative 6 pi, and negative 8 pi. So thinking about this, I know I have a sine graph. My amplitude here is 2. So normally my max and my min are going to be 2 and negative 2. But I have a vertical shift because of this +1 here. And so everything's going to be shifted up 1. So my maximum that was 2 before, shifting that maximum up 1 is going to be 3. My minimum before was -2, but if I add 1 to that minimum value for my y, it's going to be -1. My x-axis, my midway line for sine of x was going to be shifted up 1. So my midway line, which I tend to put a dotted line there, I'm going to treat like it was my x-axis, but it's shifted up 1, so it's going to be at y equals 1. So I'm thinking it's sine. Sine normally starts at the origin, but we shifted up 1, so at the start of my cycle, that point's going to be 0, 1. At 2 pi, it's positive 2, so I'm going to be increasing to the max, which is 3. 4 pi, hit the midway line. 6 pi, I'm hitting my minimum of -1. 8 pi, hit the minimum midway line. -2 pi, I'm going to hit -1. -4 pi, midway line. -6 pi, 3. -8 pi, the midway line. So from there, I have my sine graph, the reciprocal of what we were trying to graph. My asymptotes, those are values where it crosses the midway line. that +1 didn't affect where those vertical asymptotes where a normal function would have hit the x-axis. Those are still going to set the denominator equal to 0. And so graphing this cosecant function based off of what our sine function looks like, we get this graph. And I missed one, which was the y-axis is also an asymptote, vertical asymptote. So taking away our sine function, we have our cosecant function. And from here, I can see that my vertical asymptotes are when x is equal to. So notice that these values 0, 4 pi, 8 pi, that's so we can do that as 4k pi. Where k is an integer. So if we plug in 0 for k, notice we get 0, which was one of our asymptotes. If we plug in the integer 1 times 4 pi is 4 pi, I'm just checking. If I plug in the integer of 2, 4 times 2 is 8 pi, which was one of our vertical asymptotes. Plugging in negative integers, -1, 4 times -1 is -4 pi, which we have. So vertical asymptotes occur when x equals 4k times pi. And our domain, those are the values we have to exclude. Those are the values which set our denominator equals 0. So domain are going to be all values, all real numbers x such that x does not equal 4k pi. And our range, the y values that we're hitting all the y values that are less than -1. So -infinity to -1 or equal to, so bracket, union 3 to infinity. So only thing that we didn't look at when we were graphing these sine functions, the cosine functions, cosecant function, and secant functions are what are called phase shifts. That is shifting our function to the left or right horizontally. And so we'll look at that in the next section. But just be aware there is a piece in here that you cannot graph. And that's where our argument has plus or minus some constant to the term with a variable in there.